Thank you for coming today. So, sorry, the projector seems not functioning well. So some of the word might look like very opaque. Okay, so in the following 20 minutes, I'm gonna briefly talk about something I've been working on or thinking that is for the past few years. That's how to. The title looks very ambitious. Try to find the analytical solution of ensemble forecasts and using data-driven Liouville equation. And you might wonder what's Liouville equation. So I will briefly walk through this, the concept. And this is a collaboration with for my graduate student and also my former PhD advisor, Eric at CSU. All right, so three different parts for this presentation. I can briefly walk through the mass theory and test this idea in some idealized or towing models and see how it works. Because for those towing models, we have analytical solutions, so we know the ground truth. And then I'm going to apply this concept to the real weather forecast problem. And of course, some little treat, I got this idea like a few weeks ago. So I tried to connect this Liouville equation to some classical theory, and you might, maybe everyone might be surprised at how general this theory is, how generalized this theory is. All right, so before I dive right in, let's talk about something like undergrad level statistics first. Bayes theory and weather forecast, and I believe that everyone knows Bayes theory. So here are two scenarios. In the first scenario, without providing an initial condition, if we want to predict the weather on July 1st, 2025, in NTU or in Taiwan, what are you going to predict? Does anyone want to guess? Afternoon thunderstorm. Okay, summer climatology. Makes sense.
Overshooting taps.
Over 35.
Yeah, that's fair. Okay. And for the second scenario, if I give an initial condition and you already see some kind of low level jet in a Taiwan Strait, what kind of weather pattern you're going to predict for the next day?
Probably still afternoon thunderstorm.
Still afternoon thunderstorm. Okay.
Southwest Taiwan rainfall.
Sun rain. Yeah.
Maybe let me rephrase your question. Without knowing the current weather, you're traveling to Tokyo. What clothes are you going to bring?
Yes. Yeah.
Right? This is so still the question.
Everything.
Yeah. So if we formulate this into the Bayes theory, and you can see the differences between these two scenarios. So in the first scenario, let me explain this symbol a little bit. So the V here is the verification state, which is our forecast state. So the pointer right here. And I is the initial condition, and theta is the observation. So this one is read as given I, we predict, or we updated the forecast probability. So this is a forecast problem. But because for a first scenario, we don't have the information a day before, so we use the climatology, we use every kind of information we have in a history to predict the July 1st weather. But for the second scenario, because we have some knowledge for the initial condition, so we're using the observation to update our initial condition and using this initial condition to make the forecast. So this is a Bayes theory. So you can see the differences between the two. And of course, the tiny symbol here represents the entire field called data assimilation. And the second one is the numerical weather forecast.
So I'm thinking, great questions. The first one then is depends on different situations, the outflow of your distribution.
Yes.
The second one, it depends on how your initial condition can help you to narrow down your probability. But still, again, if your video originally was small enough, it's good. But if it's wide enough, then it may not be. So there's all kinds of scenarios.
Yes. Yeah. So this is good, looks elegant, but we still don't know how to do that. In real data, it's really confusing integral form, conditional probability, and you need to add it up or multiply these two probability together and get another one. So very confusing. And my focus today will be this one, the forecast problem, but it's still extremely complicated. But fortunately, we have some giant that already formulate the analytical solution for us back in 19th century, so 1838. Joseph Liouville is a French mathematician. He proposed a framework called Liouville equation. And what this equation is talking about is we can forecast the probability density function like a mass continuity equation that we use in fluid dynamics. So the first one is the traditional numerical weather prediction weather forecast model, dx dt equals f of x, where the x is the step vector, or you can say momentum, temperature, specific humidity, whatever kind of variable you want to forecast, you just plug it into the initial condition and you generate tendency and propagate forward. And then the second one you can consider as the probabilistic counterpart of this deterministic forecast. So this is the forecast of the PDF. And you can see how these two equations are related to each other. So I use this schematic diagram to explain the concept of the Liouville equation above. So this one, as I mentioned, probabilistic part. Here we have 5 ensemble member. You can see how this member, you can consider that or make some analog to tropical cyclone track. You can see how this track from T1 to T2, you can see they converge into a smaller space. And when they concentrate into a smaller space, that means the probabilities increasing over time. And then from T2 to T3, you can see the divergence of this trajectory. So the PDF decline a little bit. So the error here is the deterministic part, and that's what we already have, like NWP or any kind of AI weather forecast model. But this one is what the thing I'm working on is called Liouville equation. And if you run out and look at this figure again, you can see the density over this region is slightly less dense compared to T2. But if you're comparing with T3, you can see the density decrease more over these regions. So from this two equation, you can see how of course you can make the integral form of this equation. And now you have the density in the next time step, which is mapping directly from the initial condition. So now you see how this linked to the base theory. We have the initial PDF and we have the forecast PDF, and this is a function, mapping function. And inside this mapping function, we have the convergence, divergence of the trajectory of the ensemble members. So you can see how these two equations are related to each other. When you have convergence, you have higher density, forecast density. When you have divergence, you have a smaller forecast density. Okay, looks very elegant, but maybe it's not as straightforward as we thought, because Ed Lorenz already pointed out that in a very complicated systems, the dimension you need to deal with is extremely high. For example, the weather forecast model, we have a billion or trillion variables we need to forecast every day for every time step. So even we have such elegant formula, we still cannot use Liouville equation. And Lorenz tried to make a little bit effort on this problem, but still struggle a lot. So in this study, I'm going to use a modern solution. So for the first part, as I mentioned, we already have the AI weather forecast model. But how about we also generate an AI probabilistic forecast model for the Liouville equation? And that's the entire concept of this research. And as the formula I write down here, this model will be the function of the state. So the convergence, divergence also depends on which condition or which state you are at right now. For example, in a very clean, unstable environment, you generate ensemble, you will expect that ensemble will spreading out faster. And in a relatively stable environment, you will expect that ensemble doesn't change or spreading out that fast. Okay. All right.
So say it again, what's the subscript 1 and 2?
Oh, sorry, the one just the same right here. So,
Okay,
yeah.
Two is a
To the different machine learning model. So I also like train another model that just try to capture the entire convergence divergence right here. Yeah. All right, so there are three necessary steps to implement the Liouville equation in a forecast problem. There are three necessary steps. And of course, at step one, you need a model. So have your model. For example, like AI weather forecast model or numerical weather predictions. And then you need to find the convergence divergence. So take the derivative of this f of x, and which is calculating the Jacobian. So this can be done in a very simple way. You just build a linear regression between the input and output, and that's it. And then you calculate the divergence, which is the diagonal element of this Jacobian, and using the divergence, plug back into a Liouville equation to update it the ensemble density. That's it. That's everything. And here I'm going to provide you a very simple example as a one-dimensional ordinary differential equation which had three equilibrium points, where the 1 and -1 are stable equilibrium and 0 is an unstable equilibrium. So if we initialize with whatever kind of PDF, you will expect when you integrate the model long enough, you will expect the probability density is higher over like -1 and 1 and lower at 0. Right, so step one, have our model, and we calculate divergence also very simple, which is a quadratic equation, and then we plug this into the Liouville equation. And now I'm going to show you if we initialize the model with a Gaussian distribution, how this probability density is updated. So the solid line here shows the 5,000 member ensemble. They just generate a bunch of data and see how the PDF evolved over time. And the blue dots here are like 20 random ensembles that chosen from this 5,000 member. But I assign an initial density, probability density from this Gaussian distribution to those particle or to those ensemble member and update those density, probability density with Liouville equation. So now I'm not really using like a bunch of ensemble to generate PDF, but just make those 20 ensemble member carry their own probability density, and I use Liouville equation to update those density. And then you can see this, oh, not working. All right, so you can see this blue dots co-located with the large ensemble simulations is dying. Okay, anyway. So overall, we can see we don't really need a large ensemble to precisely estimate the probability density. And that's how powerful Liouville equation is. And the second case is the Lorentz 84. And Lorentz 84 is one of the simplest chaotic systems. And for this chaotic systems, again, we implemented 3 steps to 84 model. So step 1, we have write down the formula. Step 2, we calculate Jacobian. And surprisingly, the Jacobian of this 84 model is extremely simple. If you look at the diagonal element, it's just a linear function of x. So that means when you have x, positive x, you have the divergence of the ensemble. That also means the density going to decrease over time. And over negative x, you have convergence of the ensemble, so density will increase over time. All right. So here I'm going to show you a result and let everyone guess which one is based on large ensemble simulation, and one is based on Liouville. All right.
I think so.
Yeah, it's very hard to tell. So, so after I remove the title, I can't even tell which one is which. Yeah. So actually on the left, this one is based on large ensemble simulations. And the figure on the right is a so-called particle flow or Liouville equation based ensemble forecast. where the dot size is proportional to the density they carried. So like bigger dot means the higher probability, and the smaller dots means lower probability. You can see over these blue regions, those dots are much bigger than the ensemble over those red region, as we expected.
I was curious,
Uh-huh.
it may not be related to this, but
Okay.
for this type of PDF or this thing, can you reconstruct the PDF even in certain period of time, you lack of one variable's information?
That's a good point. So there are many statistical ways to do that. So for the unseen variable, we can have more input from the past, like have a time series. Because there are some theories says that the information from the past has the fingerprint on your variable, the state vector's tendency. So for example, if you see the change in the vorticity, maybe it, and you don't have the measure of the convective heating, but from the dynamics, you know like how convective heating generate the tendency of vorticity. So through like you can have the vorticity in two different time steps and calculate the tendency to infer how convective heating is generating the vorticity. So like you can adding more data in your input. And I also think that's the core idea of recurrent neural network or recurrent type of machine learning model. Like if you have a bunch of unseen data, but you use the lag information to like kind of compensate those lost information.
So in real life,
Yeah.
even we know this data, but it's always some essential
Yeah,
information
right.
is missing or
Yeah, and maybe we don't have those physical rules to explain. Yes. Yeah. All right, so application. Am I too fast? Okay, I just keep going. All right, so in the application, I'm gonna do something very simple. Here I use the ECNWF S2S dataset, which has 10 ensemble members, and the period cover from 2001 to I believe it 2020. I forget to put the information right here. But since the model only has 2 ensemble members, that means if we calculate the Jacobian, we can only constrain like a 10 by 10 matrix. We cannot do something bigger than 10 by 10. All right. So first thing I'm gonna do is decompose this field, like forecast field, into 10 EOF modes. And then I'm gonna observe how this 10 ensemble member propagates in this 10-dimensional space. But I don't know how to plot the 10-dimensional space, so I just plot the 3-dimensional space. All right. And then by calculating convergence, divergence, I also train the machine learning model where I use the state, which is the PC, the time series of this mode, as predictor to predict the convergence, divergence of this trajectory. And that's it. And to systematically visualize the result, here I use something called attribute diagram. Looks a little bit complicated, but it turned out the idea behind is the expected value. So let me explain a little bit. Where the x-axis is the forecast probability, and y-axis is the observed frequency. For example, if today you're gonna forecast the mesoscale system or May front, that kind of system, and 70% of your models say yes, the Taiwan Southwest gonna be influenced by this mesoscale system. Okay, and if you make this kind of forecast 100 times, then the expected value will be 70 times. You would see the Taiwan gonna be influenced by this mesoscale system. But if the observed frequency is lower than 70, that means your model is overconfident. And if the observed value is higher than 70, that means the model is underconfident. So a perfect forecast is that your forecast result lie along this diagonal direction. and that's called reliable forecast or perfect forecast. And using Liouville equation along with the ECNWF ensemble forecast, we can see even up to the lead time of 40 days, we can still have the probabilistic forecast aligning along this diagonal direction. So that's pretty promising. I don't have like the traditional ECNWF attribute diagram, but pretty much every model get flat after day 20. And this one, if we implement Liouville equation into ECNWF reforecast systems, we can see at day 40 we still get pretty reliable probabilistic forecasts. All right, so as I promised, I'm going to give you some little trait about something I've been thinking, how to link this Liouville equation. Because it looks like a probabilistic forecast method rather than a real physical theory, but maybe you will find something like surprising. Here, I'm going to use the blocking at mid-latitude as an example. So this is from Nakamura and Huang 2018, the paper they published in Science, where they developed a towing model that described how traffic jam happens in highway, and use this traffic jam models to describe the blocking mechanisms. So the concept is very simple. Use the QGPV equation in the exotropics, and we can write down this equation in a matrix form. And for this very ugly looking matrix form, we can derive a more ugly looking prognostic equation for the PV variance. And for those who are familiar with GFD, the variance of PV or variance of vorticity is called entropy. And in large scale community, they call it wave activity, but it's a similar idea. All right. And I'm going to show you in a moment how it's related to Liouville equation. Since we're like linearized the system right here, to some degree, we're implementing Gaussian assumption. Okay, so we have Liouville equation, and if we implement Gaussian assumption to the probability density here, and we substitute this probability density function back into a Liouville equation, we actually can get two identical equations for like a probabilistic forecast. So for the first one, we forecast the mean, and the second equation will forecast the variance, which is the entropy or wave activity right here. So you can see when we forecast the Liouville equation, we are actually forecasting like different moments of the PDF. So it's a very powerful tool, not just a weather forecast tool. And this can be applied to other like things we've been working on in our field. For example, convection aggregation. Because convection aggregation, we are looking at the more steady energy variance. So we calculate variance, see how the variance grow over time. When we have larger variance, we have more aggregate convection. And so the same idea can also be applied to this problem. And also the vortex-Rossby wave, and because the dynamics is very similar to the mid-latitude jet, so we pretty much can apply the same concept to this kind of mechanism. All right, that's all I have today.
So just quick, when you talk about vortex-Rossby or talk about this, would the inertia or the coherency of this property measures? I mean, like
Yes. Yeah.
You know, vortex-Rossby, some may be highly dispersed, but some are very coherent.
Right. Yeah, so if we go back to this equation, sorry, it's oversimplified, but the A here is like pretty much you put the linear operator, write down the linear operator into this tiny A. So it shows how your 80 interact with the mean flow. So in the vortex-Rossby wave problem, is how your those waves interact with the tangential wing. And yeah, but if we look at the prognostic equation for this covariance, it actually has a source term. So something I didn't mention here, Liouville equation has a counterpart. It's called focal plane equation, and that's the equation that doesn't follow the conservation law for those systems that have like source or sink inside the model. And I think the tropical cyclone is more like the focal plane problem, where we have like source and sink, and also.
Because what you showed there is linear equations.
Yeah.
But if you're looking at, there's two possibilities that the linearity may break down. One is time scale is long enough.
Yeah.
And the other one is that internal dynamics generate a very sharp gradient.
Yes.
That leads to coherency if survive and all these kind
Yeah. So like we probably need like the second prognostic equation for forecasting the tangential wind, how they change over time.
Another thing, I'm sorry, I could ask.
Yeah.
I always follow with this, but maybe you can comment. I use it for you.
Yeah.
So you have this the obvious equation, right?
Yes.
Like this, right?
Yeah.
But what about if you have an equation like this,
That's a good one.
right? It's something like this, but this is localized, right?
Yes.
And then you can write this, I think it's if your this is also related to somewhat to your density. Right? So this is some kind of information for the wave speed. But
Yes,
only
yes.
this, and I know you're talking about the wave equation.
Yes.
I'm just curious about this.
Yes. So there's one series called Kleeman and Liang theory. Sorry, I need to use the pointer right here. Kleeman and Liang theory. They look at, so let me go back to the schematic plot. They actually have the method that enable you to visualize how the information propagates in phase space. And I think that's what you are mentioning here.
Okay.
Yeah.
So there's a paper.
Yeah, there's a paper already published like almost 20 years ago. They're working on this. Yeah.
But still, but then the similar thing.
Yeah.
I
similar
think
thing.
it's a great example of this data sets.
Yes.
Give us to do. Okay.
All right.
I'm not sure if I follow correctly about the idea of applying the equation in community application.
Yeah.
So
Let me go back to, sorry, right
So
here.
what it means, we need to like decide the mean field and the covariance for this question. Then we can examine that concept by using Louisville equations.
So rather than saying applying Louisville equation to convection aggregation, I would say like any kind of equation of calculating covariance can be linked back to Louisville equation. Yeah, so it's like the same idea. So that's why I want to say that Louisville equation is a more general concept of describing how PDF change over time.
Okay.
Yeah. And I know a lot of community calculating the covariance or variance over different variables, some calculating in more steady energy, some calculating in vorticity, and that's, yeah.
So with the overall result of this, if you're going to do this study?
I haven't, yeah, I don't have the color resolving model, so I haven't done it yet.
Here's the
Yeah.
But I think this is interesting because I'm working on the topic cycle to see this, but maybe this part is always wondering how this density related to the helical flow.
Yes.
How helical is the flow.
May I ask you?
Yeah, sure.
Could you go back to the overconfident?
Oh, yeah, no problem.
Yeah, I found this is very interesting. And I have a question. So why is the curves goes from underconfident to overconfident?
I think, okay, so I'm still not sure if that's a problem of like how we implement Louisville equation into ECNWF system, or is the problem of ECNWF system itself. Yeah, because a lot of time is a lot of people blowing on ECNWF on some forecast, their spray is too narrow. Yeah. So a lot of time their model is overconfident. But with the increase of forecast lead time, the spray is getting wider and wider. So yeah.
Yeah, this is very interesting because I'm thinking about when the low probability means extreme case.
Low probability.
In this diagram, the low probability it means extreme for example, extreme heat.
Oh, this
extreme
is
rainfall
not
case.
like about the extreme or it's about like how many ensemble members agree with this event gonna happen. So it can be both extreme and non-extreme case.
Okay.
Yeah.
Thank you.
So I'm still in the scenario of you having the colors of your model.
Okay. Yeah, I can go back to that one. This one.
So, okay, let's assume, and you do
Yeah.
have the colors of your model.
Okay.
So, in your opinion, what would be the experiments? I mean, what experiments would you design to see if the covariance of integrated MSE can be like somehow explained using the Review equation? Would that be like the initial condition of the boundary layer, or like additional setup or LC interaction?
I haven't thought about it yet, so maybe we can discuss. And I think for like any kind of self-aggregation, as long as it aggregate,
Okay.
and we can apply this framework to study how the information propagate. For example, if the model has very strong like convective radiated feedback, or like through some kind of moisture, I forget the name, how the shell accumulates moisture. Shallow circulation moisture instability, the kind of mechanism. Yeah. And we can go back to the Louvier equation right here. We have the AZ here that describe all kind of positive feedback or interaction right here. And then we can see how this like certain process information from certain process propagated to the other processes. For example, at a given stage, you might see the convective radiated feedback is the dominant process to generate variance. But at another stage, you might see that different processes might dominate the increase of the variance. So the information will propagate over the process, the state space. I don't know how to describe that, but like different axes represent different physical processes.
I'm curious, what is no, I may not ask properly, but what is the time scale you're thinking, the common two characteristic time scale of your physical system?
Okay. So for each dynamical system, we need to, yes, I agree. This is a very good question. So for the forecast problem, or the problem we deal with, how the PDF evolve over time, we usually define something called error doubling time. So how the initial error doubled, like how the variance doubled in a certain non-dimensional time. So we define that, the error doubling time as not really non-dimensional, but like a standard that we use in forecast problem.
Yeah.
Also, so like over different problem, we have different error doubling
and
time.
also in this kind of, if you're looking at well, usually I think the mathematically, I'm thinking is that sometimes time scale is the nonlinearity becomes important.
Yes.
The blocking.
Yeah.
Sometimes it's not that long time scale, but due to the function is smooth.
Yes.
But the derivative of the function becomes sharp.
Yes.
So nonlinearity becomes stronger. But in order, when you're doing this kind of a lot of prediction, there's a lot of way you can play around with it, like because they usually use auto regression.
Yes. Yes.
Thing.
Yeah.
So that may be the AI keyword, at least to a certain extent, try to alleviate the accumulation of your error in your model.
Yeah. Yeah.
But on the other hand, if you just tune your model with reduction of the autoregressive, as some of the Chinese model, they claim they gain 1 day compared to the European center. But I think that at an expense of, this large mesoscale or extreme type of thing, the variability just totally missing from the forecast.
Yeah.
So my question is that, I may not ask properly, but I was just thinking that in terms of reality, there seems to be two choices, right? You can try to make it as smooth as possible.
Yeah.
But missing a lot of important mesoscale, but you may also want to have
Yes.
certain natural scale,
Yeah.
but then missing some of the thing and you use that as a sample. Would be somewhat related to your
Yeah. So I think that's how, that's the most, I won't say the trivial, but like maybe not cherry picking, but like how we choose the variable right here is very important. Because if you choose the right variable, you some kind of filter out the high frequency signal. And if you choose the variable that can represent a lot of high frequency signal, you are more talking about how the error grow in a short period of time. Yeah. So like how we design this, how we implement the variable right here is very important in C. Because they are depends on how PDF change over time depends on the function state right here. And
also maybe what's a variable is a Gaussian or non-Gaussian.
Yeah. And for like very simple Markov chain or like linear autoregressive model, that's the Gaussian assumptions. So it pretty much talking about you can consider that as a slow varying systems, but if you make the system have very short memory, like a white noise, and still implement Gaussian assumption, but like the system will saturate it into like a random white noise very quick. Losses information in a few time steps. So how we define this variable is also the key in this problem.
Thank you. I've been hearing your talk several times, but every time I feel great. Every time it's a new talk.
Yeah.
There's a lot of new information every time I hear from Kai-Zi. And yeah, thank you.
Okay.
I really appreciate it.
Yeah.
Right. Oh yeah. はい。这个不知道够不够。不会。
我觉得就是越来越
对，前。
而且这些 fundamentally 我们关心的这些所谓的问题，看起来这是一条就是蛮有趣的。
我还在 convection application， 所以就是对我比较熟那个方面。所以变数的选择，我们要首先了解那个变数本身的time scale 变化的time scale 大概是怎么样。那像是假如是 integrated MSE 的话，我们已经知道在特定的模式，它可能对于 aggregation 只有 aggregate 有一个特定的 time scale。那测试不同的变数，
应该说，如果你要看 NSE 的话，应该说，如果你那个 model 设置在 Java， 对，然后 for those scores 非常小的时候，你用 temperature 可能就不是一个很适合描述 server aggregation 的东西，但是你用 moisture 或 NSE 的时候就很好。
我是对我是in the future， 对啊，就是我们台湾真的在这方面就是有大机器，有非常好的统计力学跟预报度的课程。因为在物理系的他们讲的那一套，当然很有趣、很重要。可是我觉得这个是应该是 cutting edge 的东西。
最喜欢的一门课。
我们是真的开始应该要创新，就是我们有这种是吧？我觉得开始
就是分子气体，
当然真的是可预报度
不能说简单，但是他们都弄完了。
那因为大气科学非常适合撇开那些古典的
对，统计力学，
真的
把它抓起来。
困难，然后他会考虑很多，像你要 worry， 像训练在问的，你要 worry 什么，你要考虑什么？那这里面其实有很多统计力学的东西，可是他们又没有那么绑在可预报度或预报的问题。我这很热血，我要开始建议。
总之这边有很多 run 可以算一下，就这么简单。
除了下面以外，我们也有很多，应该是说算是机会可以拿气象书的，像是 GPS， 然后一些 example， 感觉起来好像，假如经过一些适当的处理，不管是 smoothing 或是都可以靠。
这我自己在，就是在心里面就一直在想，我一直觉得我们是需要有机动力学的更好的方式，但是我读很多这种的，就是3号没有，我就非常开心看开支程度。We're talking about. I think eventually they should maybe 开支 should have a course or class of the statistical dynamics and the predictabilities. And I think that would be an interesting contribution.
Oh. I would like to take that class. Yeah.
Okay, let's move on to our next section. Our next speaker is Professor Jamie Wu.
Okay.
And Professor Wu will bring us a very novel idea of how to connect AI and extreme weathers in Taiwan. Let's welcome Professor Wu.
Okay. So, yeah, because Kaiju show a lot of something new, so I dig out my desk, I draw and find something new here to show you. And as Professor Yang mentioned about the TAOP in previous sessions, I found I really did some Vivian simulation of this TAOP days. And that's one of the snapshot of the radar reflectivity, weather station precipitation, and time Vivian simulations. So as we are interested more in a storm mode, so you can take a look at the high-resolution simulation on this afternoon thunderstorm on the right-hand side and the radar reflectivity on the left-hand side. So you can see that this is overshooting structure clearly appear in this thunderstorm simulated by the VVM. And very interestingly, the simulation is done without data assimilation, without even given any horizontal information on the flow field. So that's what I'm going to talk about next, is what we think, or what I think about this time Vivian, and then how does we go from here to the future for this weather prediction. And of course, focusing on the Taiwan's topography, and how do we use that as an AI and for the physical interpretable AI framework. And everyone shows a picture of a group, so I show a picture of two groups. So this is a group with Wei-Ting and me somewhere here. So I want to demonstrate that in the future, we have a lot of fun study going on, and all the students here are PhD or postdoc. So you don't know them right now, but you will in the future, very soon. Yeah. And everyone has an expert in many different things. Some are in AI, some are in observation, some are in the numerical modeling, some are in the data analysis or everything. So very exciting to share with you that in Taiwan, in NTU, we now are a strong team on this convection, climate change, and AI, everything. Okay, so yeah, just let you know that. And moving on to the time Vivian simulation, afternoon thunderstorms. So it's very challenging for this simulation of afternoon thunderstorms or prediction of afternoon thunderstorms in Taiwan, mostly because of the complex topography. And it's always how we said, tell the public the topography is so complicated that we cannot predict the afternoon thunderstorm. But on the other hand, I found it is an interesting argument. Maybe it is the other way around. It's because the topography is so complicated, and if we can handle it correctly, we can capture the afternoon thunderstorm very well. For example, we are showing here is the afternoon thunderstorm over the Zhenwen water reservoir region. So you see that this afternoon thunderstorm is very different from other places. It started in the afternoon and it can last almost till 11 p.m. But it sort of dies down afterwards because there's no large-scale system supporting that. And you see that the precipitation happens mostly over the mountain area, supporting the water dam over there, the Zhengwen water dam. So this kind of precipitation system sort of is a major water resources in the summertime in Taiwan. And we want to know that how does that change in the future, and it's important in our Taiwan's water resources. So we need a tool, we need a model, and we need an idea to understand what we are doing. So the first of all is we developed the Taiwan VVN in-house here. And it's very different from other models that they predict the inelastic vorticity dynamics. In that sense, you see the vorticity equations directly predicted in the model. And the most important of all, we predict the horizontal vorticity. So it represents this convective structures directly. And it will respond to the Born's gradient based on either condensation or surface heterogeneity. The second thing is that we implemented topography not just by numerical approach. Instead, we use topographic forcing added to the vorticity equation on the right-hand side. So it's embedded in the dynamics of the system, so that it seems that if you see topography here, you actually see the added vorticity at the corners of this topography. So the flow pinching the topography, it sort of generates counter vorticity, putting back to the vorticity equation. And the most important of the part is that the vorticity predicted, but the velocity is actually diagnosed through this 3D elliptic equation here. So you can see that if you add the vorticity in the model domain, the curve of the vorticity will generate a ring structure of the vortex. And by solving this vertical velocity elliptic equation, we can get the non-local structure of the vertical velocity generated by this topography as well as the mean flow. So in that case, the vorticity dynamics and the orographic effects of the embedded in this dynamical equation, so that you don't create additional numerical problems when solving this inelastic equation set. And that's sort of the uniqueness of this VVM model, in that given any resolution, as long as you give it sufficient computer resources, because if you have higher resolution, you need more computer resources. Then it will generate a reasonable flow associated with the topography. A good example here I show is that we see that this is afternoon thunderstorm cases from the Weather Bureau stations. And this is the time VVM ensemble simulations. And the other one is, as I mentioned previously, we want to know what happens in the future. So comparing the current climate simulation and observation, you see that it captures the afternoon thunderstorm very well. And that gives us we can trust the numerical simulation for the future climate simulation with the time VVM. Okay, so what is topography effect, or what is topographic forcing I mentioned here? So what I think is that there are the added vortices based on these boundary conditions given in the inelastic flow field. So if we can quantitative calculate the orographic forcing, it would be nice to tell us what really the mountains are doing in this flow field. So what I do additionally is to calculate the vertical velocity sort of generated by this added topographic forcing. And then we can visualize or quantitatively discuss how the topographic forcing is. So to show you an example, I use a pretty 3D plot for this case. And this is a wintertime environment. You see that it's a strong northeasterly environment case here. We are looking from the north to south. There's Yilan here, so there's a Datun mountain here. So the central mountain is over there. So the flow field is something like that. It's a real case, so you got different shear and structures here. So the color you see here is the vertical velocity calculated by solving the elliptic equation. And you see that a lot of multi-scale structures. First of all, if you have a strong northeasterly flow, you expect it to have some up and downs of the mountain regions. Maybe you expect it, maybe you're not. I'm not sure. But in Datun Mountain, you see that it's upslope here and downslope there. So you see that the fine structure difference here. And if you change the wind direction slightly, say it's from the strong northeasterly to slightly weaker and northerly wind flow, you see that the vertical velocity topographic forcing is very, very different in these two scenarios. And you see that the major upwind motion is very different from the previous condition. And if you give a different strong northeasterly regime, you see that again, the up and downs over the mountain regions very different. And the major structure also changes during this different wind regimes. So previously in the textbook, we always know that there's a flow number dependent, but it's directly responds to a mean upstream flow and isolated mountain. But now we don't have isolated mountain, we have thousands of mountains here. How do we measure it? How do we quantify the topographic forcing? I think VVM provides a good opportunity to show you that the different topographic forcing caused by this upstream flow and downstream development. Okay, so that's sort of the interesting part of this orographic forcing in Taiwan, and that's why we always don't know why it's so complicated to know how the topography affects to the Taiwan's any system precipitation or this flow regimes. Okay, so following this trend, if you want to know the air pollution in Taiwan, we need to know the flow structures in Taiwan. So in the winter time, if you have a very different wind directions, here, you see that the tracer transport will be totally different based on the structure of the flow regimes. And you can see that if we have using the Taiwan VVM to perform a variety of simulations, we can generate a lot of data. And the data is solely controlled by these upstream soundings. So in the model, we sort of implement only this upstream sounding condition. So it provides temperature, moisture, and the wind field and vertical structure. As the flow comes to the Taiwan, the topography will control everything to generate local structure of the vortex or this flow regimes. And based on that, we can generate maybe like 200 or 300 cases, 200 cases here to demonstrate that the different flow regimes respond to the upstream sounding conditions. And then that we call this AI-ready data set right now because it's almost impossible to measure this kind of flow regime over the ocean or over the mountains. So we use this time variance data as AI-ready data, and we can use this machine learning approach to learn from this data. And if we can duplicate the time variance 100%, we will call that an emulator. But normally that's a dangerous way of calling that because the time variance simulation is sort of limited cases, and in a selected weather regime. So what we think is that we need something to sort of distinguish what we are simulating in a upper level. So we have to decide the weather first. For example, we want to decide the local circulation dominant weather here. And then we want to know that in this kind of situation, can the AI learn this simulation easily? So we sort of separate the weather regime, not just a full powerhouse emulator to generate all the weather. We want to have different weather regimes defined by us, like to make sure that the AI can learn the details of each weather regime. It's because that for different kind of weather regime, maybe we are focusing on very different things. For example, in the winter time, this air pollution regime, we don't really care about the precipitation. So the precipitation, the area of precipitation is not a major concern in this kind of system. And in the summertime, we may not worry about this leaf vortex. So the leaf vortex flow dependence might not be a major concern of our the information we care. Okay, so that's kind of the idea of the flow. So we choose the weather type, and we make sure that the details of the weather type we care can be captured very well, and then we can use the AI model to do that, to learn that. And most importantly, the AI model we use is always something like this. In fact, almost every kind of AI model looks something like this. So there's an encoder and decoder. So the encoder sort of compress all the information to a very low dimension. And then based on the low dimensional data, we can generate the real flow field based on this AI model. It's something like we learn from the data to some kind of principle of physics. Maybe that's too much, but it's something similar to that. But anyway, the dimension is reduced so that we can try to interpret the reduced dimension based on this AI model. So in this case, we reduce the dimension to 2, so two numbers. So we can interpret what the 2 dimension mean in this leaf vortex simulations. So we found that actually it represents very fundamental dynamics. It's for wind direction and wind speed based on this reduced order, this latent dimension here. So now, if we know that, we can sort of generate the flow field based on our input information. So right now, if we have a northeast flow, we can put it here, and we can generate this 2D flow field based on this input information, upstream information here. And if we want to do more, we can use a more complicated model, but the explainability reduces, but it will be more like a simulator. So this is a different study. So we use a more complicated AI model so that it can learn the 3D full vertical structure of this wind field based on the upstream flow. So here we only use the near surface wind to explain what's going on. But now here we can use the whole sounding wind direction to predict everything near the surface wind flow. So you see that the prediction sort of match the simulation pretty well. But because the complexity of the model, it sort of loses the explainability at this point. But again, if you trust more on this time vision simulation, we can call this kind of an emulator. And we can use that to generate even more detailed structure of the flow field. But if you want to predict the future climate, I would suggest that some explainable AI is more feasible in this kind of situation, so that we know what we learned from the AI model and use that for prediction. Okay, so this is the last slide. So what we think about the AI is actually more simulation of from numerical models. And the approach we adopt is a storyline based. So we choose different kind of weather regime to have very different time variant simulations. And for each kind of weather system, we are focusing on very different topics, not necessarily precipitation, sometimes the pollution, or sometimes the dynamic cycle of the mountain valley winds, etc. And the key of this time variant simulation is that we use the upstream information to generate the flow field, because we are thinking of this upstream downstream development is caused mainly by the topography. So we can allow this topography to dominate these variabilities, and it just take the upstream information from these soundings. And the better part is that in current GCN simulations, Taiwan is just probably 1 or 2 dots. So it's probably impossible to do this downscaling based on only few dots. For me, I just need the sounding. So if you give me a sounding from the GCN, I can generate similar things based on this airtime variant framework. And then for that, if we can do trust the results with we can trust the AI result by providing more explainability. Then we can use that as a generative model to generate any weather we want. So this is a scope of airtime variant I'm just starting to know. And this is sort of wintertime is a published paper, but summertime we're just starting. And now we are having more extreme precipitation scenarios right now. So I'm happy to see if that will fit the observation or provide better prediction in the future. Thank you.
Can you show in the very beginning of the observation in the macro simulation?
The Tahoe one?
Maybe Tahoe one is okay. It sounds a little bit difficult, critical, from the operational point of view. We often concern whether that precipitation occurred on the slope or even slightly deeper into the mountain. And a slightly deeper into the mountain that can have important water resources for the dam. So it's a subtlety you can see in observation. And also the other thing is that it's often in the model, because you are mainly from the topography forcing. So in the sense that there's a lot of precipitation over the land in the flat area, it may not be there. But then it comes the argument or the question is that it's not just a topography, it's just not sounding. Sometimes the mid-level moisture inflow is important to prolong the precipitation or second run or that kind of things. And even in this summer, we have a monsoon trough in India with a typhoon, and which is very, very heavy, 20 kilometer deep of the convection. And that kind of thing, I'm just curious, appear not in the simulations.
So
and when you're talking about the future weather, the role of the topography is important, but what about how do you know whether you're going to have an AI atmospheric river?
Yeah, we'll always have a version 2 of these simulations. So,
I mean, this is a kind of a clean case of
So
synoptics.
So again, now we're interested in the strong forcing environment. This is 2 months ago, July. This everyone's favorite southwesterly for 8 days. So you see that this is similar simulation. It's driven by soundings, but I sort of change the soundings from day to day. Just allow the previous study is like one sounding for 1 day. Right now I use a continuous evolution of the soundings. So it's still sounding driven in some sense, But now you see that the wind direction changes and the moisture supply might be very different from day to day. So it's, from in the previous, the afternoon thunderstorm to me is something like a one-day event. But for this kind of southwest flow, it's not just one day. It's sort of night to day to second day follow-up. So you see that in the simulation, you see the very different evolution of this plane precipitation. See that again?
Yeah.
Yeah. Plane.
I guess, just from operational point of view, that in the land or over the slope or over the mountain, or in the late afternoon or in the early morning. And but surely this is the summer. Maybe Jim will comment. I always like what about when the SST gradient exists in the southwest of Taiwan, and then you have a different marine boundary layer if you not have proper interaction? Would that also be affecting the precipitation things? Because I know there's no AS interaction over it.
There's some AS interaction. Yeah, but it's I use the fixed SST, so it's not the full interaction yet.
Yeah. Yes, some technical questions. So for this one, you are changing something every day. But when I read your papers, that you do the one-day simulation, first 3 hours that can speed up time. But how about this case?
So it's continuous simulation. So in the previous study, I always do the one-day simulation because of many things. Because first of all, I think the afternoon thunderstorm is so limited in one day. And the second thing is that it's easier to set up an experiment. But for this, it's sort of continuous simulation throughout the 8 days. So if you treat some time spin up, so I skip the first few hours, don't worry about that. It's just something not ready yet. But for the later days, it just carries all the information from previous.
Your second day, some days advice more like the data simulation.
That's a two poor man's data simulation, just a nudging of a sounding. Yeah.
But the summer one is interesting, though this is very intriguing. But I think if you move the time a little bit earlier in the June, that sure, one thing, the SSC gradient that exists in the southwest of Taiwan as a boundary layer is important. But I think also, I haven't seen the Q1 analysis in the summer, but there was a Q1 analysis by Dick Johnson. So it's showing that indeed in this weak synoptic you have a thick convection near the mountain, but you take a Q1 probably doesn't matter on the slope or on the big mountain. But then in the day afternoon there's a straight form. So in the midnight, 8 o'clock evening Q1, it behaved like a straight form type of Q1. And then in the early morning, Dick Johnson showed that it's a cumulus congestions. So the heating was in the lower, and it's possibly come from the ocean. So anyway, I was just curious if this kind of things that not seen in the summer, but maybe that's a seasonal difference. But again, I said, Jim probably was, what about radiation?
Yeah, more analysis are needed. Of course, this is a proof of concept about how the framework can apply to different kind of weather systems. That's what I'm demonstrating right now.
I think it's very nice.
Yeah, I guess kind of going off of that thought, that's one of the regimes I think about in kind of the early summer, when that frontal region is kind of across like the southern part of the strait, and you get these really robust, long-lived MCVs that develop, and so they might be producing some of their heaviest rainfall and growth period over the ocean, but then of course have major impacts over southwest Taiwan once they make landfall. But I wonder if even a sounding can capture that if it's in a placement where it sort of indicates that low level big change in wind direction. So there's an indicator about the regime that there's a change in air mass, and there's implied a really strong shear zone to the south, and that it would produce this highly variable rainfall. I'd be curious to see what that case would look like, since it's much less regulated by the diurnal cycle and the orographic forcing. But yeah, I think it's a really nice demonstration of case, and I think we're just excited to see more.
So what I'm thinking is that for the sounding, I didn't specify which sounding or where it is. So the choice, how to choose the sounding is sort of the main topic I'm working on. How to do that, how to define representative upstream information to Taiwan. So since we've only focused on Taiwan's precision for this topic, so we want to know the upstream information. For example, if you have a strong southwesterly flow and in the frontal region, if that thermodynamics and the vertical wind shear already tell us a lot of the information, maybe we can generate enough precipitation over Taiwan. I'm not saying like 100% accurate, but it captures the main features. That's sort of the first step of this kind of study. And then if I choose a sounding wrong, for example, if I choose a Taipei sounding, maybe I got nothing. And I also did a lot of simulation demonstrating that. So if I choose it wrong, it's catastrophe. So that's kind of fun, right? Because the simulation is only driven by upstream information, but which upstream information give us some thinking process so to find the most important region.
But for the long time ago, I did some study. I didn't publish it. That I found out in the southern part of the Taiwan during the summer, you have a afternoon very heavy 40 millimeter above thunderstorm. Most of the time, they are associated with the atmosphere to the far east. So that will not show sounding. And also I think in the summertime open, we also have to look at the cocoa ball if they are available in Taiwan. That also can dramatically change the story. But no, I'm just talking about future weather. I'm just curious. These factors are important. What the future will like.
The fun part is if I show you a typhoon simulation just with the sounding. Next time you'll see. That's kind of thermodynamic view of this simulation because the environment provides energetics and wind direction only, wind speed of course. And then you're thinking about everything's moving around in Taiwan, so typhoon hitting Taiwan or something. But at the end, the precipitation happens where the flow intersects with the topography. So that's this ambiguous part is what I'm looking for. The Taiwan has so many complex situations that we have right now. There's a low pressure in the northeast, and then rain for so many days. But still, if we can capture that information with only fewer dimensions, then it will make the interpretation a lot easier.
And also, I think this is I'm not so sure, maybe something can be seen in the VVM is the conventional wisdom by George Chen. They keep on telling us, anytime you see the westerly in the Penghu, you should very care about the deconvection. And so it turned out the one I showed you, 20 kilometer high, that was the situation that the Penghu was westerly.
Right place. I always want the forecast knowledge, like experience, to tell us which upstream to choose, and then I can test it to learn more about the evolution of the convection.
Ken always said that you look at, but that's a rare event. You know, you come to, so people begin, you know, like we certainly worry about the southwesterly inflow of the moisture, but that, again, that was a control, maybe certain to a certain extent, but into a seasonal or seasonal type of things.
I also wonder, so you showed that these two dimensions are, they correspond to the wind direction and wind speed. So I'm curious if, and maybe this depends on, like which season you're focusing on, but at least in general, we would think of like one of the important dimensions should be the amount of moisture.
Yes.
But do you think that's not one of the key dimensions here? Because we sort of assume like it's basically that's not a key variable. It's always available, and it's just about where the wind comes from.
So that's a good question. So that's how I sort of separate the winter weather into this pollution dominant. So it has to be dry, otherwise the pollution won't stay here. And there's also the preceding northeast part, like these days situation. So that at that point, the moisture is so important. I'll have to include that in the dimension. So you see that I'm making doing the puzzles. I didn't have the full picture yet, but I know the pieces, and I'm trying to make it as a big picture in the future. And so more suggestions that will come. I will look into that, and I'll do more simulations.
So you say again, the resolution you use is
So for the typical simulation is 500 meter, and the vertical is 100 meter.
Yeah, that's not a cheap experiment.
That's not cheap at all. So I usually only have like 3 simulations. I have to write a paper. So that this paper in the beginning, this one is only I have 3 simulations. I have to write a paper. It takes too much resources.
Just last few months, I'm covered with AI project, and
Yeah.
very good, decent simulation, but it cost some $4 million or something of the Taiwanese dollars, so that amounts to $100,000 US dollars of the computing time. It's only in a few months.
But for that, Taiwan put assets to pay a lot on the computation compared to the US. For you, if you're using derecho, it's probably free.
We should hack into derecho.
So if you get an account, please let me know. We can do some interesting simulations together.
Well, then I have good news.
Okay, good. You see, we are limited on the computer resources, and so it's very challenging for us to do this kind of high resolution simulations.
There's always in Taiwan, when we try to, as senior scientists, I always try to keep on telling outside people. They say, we want to develop AI, we want to use a GPU. But I say, well, you cannot build a CPU. Right? The AI ready data is so important. So don't forget the CPU.
Who provides the computing in Taiwan?
We have a national computation, high-speed computation.
High-speed computation center. So Jimmy and I cooperate with the AI model. We set the priorities and put them on money there, so we're limited time. You have always the first priority. Otherwise,
right now you cannot run. The total resources is limited, and you need to put a lot more money to get like resources. So it's pretty challenging.
So that's one of the things that as a theoretician, I mean, just like Wayne, I was back there thinking and reading, but I keep on pushing myself to get a huge project. I think one of the things that I know that then I can have a good team. they can contribute to the science, and they need the computing power.
Yeah.
And that's kind of expensive.
Yeah, okay.
Yeah. Yeah, and the provider doesn't know that we need this much of resources. They always say, "I think it's enough."
And nowadays they prioritize on GPUs, right?
And yeah,
They always talk about. I think it's take time to, because I need to be, I learn to be patient because I'm an old people. Well, actually I don't feel old, but my age is old. I see the Taiwan grow from a kind of third world type of thing to today. But still, I think you have to talk to the manager. This manager, so that they can appreciate, even they want to develop AI, they need good observations.
No.
And that's why we learning helps a lot, try to allocate the observation. And I'm hoping eventually they will allocate a huge amount of computer time for our meteorologists.
No.
Because we want to develop what they like, great AI.
No.
But, so that's why Bobo is not here this morning, because he came to go to fix up something.
Negotiating.
Well, just explaining to the people,
Yeah,
because they are not meteorologists.
the knowledge transfer is pretty hard.
Okay.
Knowledge transfer,
Yeah.
telling people that we are doing the right thing.
I appreciate all the, our department helped me a great deal. I tried to get this project, and the last year when Jamie was there, we were struggling real hard with the computer science people.
Yeah.
But it goes totally opposite. That the computer science people totally back us out this year. They think we have a good idea. So we just have to be patient.
Okay.
I really appreciate it. Jamie did a lot of these things.
No. Yeah, it sounds like the car ride and the hands-on experience with how much effort to maintain the instruments and everything. We need to find the equivalent of that for how much effort and time and patience it takes to run the simulations and develop the code, refactor for GPU, all of these steps.
So it's something like when I was in CSU, it was a time I was greatly inspired by this using the numerics to solve for the PPE numerical model. So it's almost my whole career, and now I'm so excited about the AI. But then you just have to, you're facing the different people. In the AI era, you need a GPU. You have to explain why CPU is so important. And they'll ask you a question, is the numerical model going to vanish? Or, what are we going to do? You just have to keep on, just like an educational type of thing. But you have to defend and to tell the people. And so that's happening. I don't know, in the US, probably they will not ask that kind of question like, is numerical model going to vanish and everything go to the AI?
Yeah, but the decision's just made for us by the administration. So it changes, it comes and it goes, and it does feel quite out of our hands. But I think, I think a lot of the people who are involved in leadership of places like CIRA, so a lot of the cooperative institutes for NOAA, like the leadership of those institutes, try to get the ear of politicians in Washington and keep reminding them that, especially when it comes to extreme weather, we're very vulnerable and it's not a solved problem. We cannot rely on just private business. Of course, private industry is very important, but we need to continue studying these problems and we need to continue having the resources to do that. But yeah, ironically, it's the years where it's been Republican administration in the US, the weather funding has actually been higher. I think because a lot of the red states, a lot of the more Republican states are so affected by severe weather, by tornado outbreaks. So it's one of these things like weather has a way of defying what your expectations are and reminding you of reality, whether it's politically convenient or not. But right now we can't really make sense of any of the pattern or have any prediction of what's going to happen in the next couple of years. But at least historically, whichever way the country would politically swing, it would either be more funding towards weather or more funding towards climate, but still a sort of a respect for the value and importance of continuing to fund both the operational and research sides of things.
Yeah.
But I feel it's a low predictability moment.
It's a big base for, Florida, right?
Yeah.
Typhoon, hurricanes.
Yeah.
Other than all these tornadoes for the US.
Yeah. Yeah. So we will see. Yeah.
And let's wrap up this session. Thanks again for the wonderful comments and
Discussions.
This session. And our next session will be chaired by Professor Hubert.
Thank you.
And he will bring some thoughts about radiative feedbacks and cognitive skills. I'm sure we are all very interested and excited about this topic. And so there's welcome, Tim.
Thank you. Let's see if this shows up. Okay. I'll try to watch my time too. So it should be 20 minutes, 40 total, right?
Maybe just tell me that our lunchbox are late.
Yeah,
so.
Convenient. Perfect.
To discuss and
Yeah.
I think the purpose of the workshop we presented, we talk to each other.
Yeah.
So don't worry about it.
Okay.
I think especially due to unfortunate situation, Pete is not here, so we definitely
More time.
So don't worry about it. And we can
You can
still
take up
talk to
John's.
each other.
Yeah.
But anyway.
Yeah, I mean, I still kept the name NTUxOUxPennState Joint Workshop on AI and Convection. We miss you, John. Yeah.
Penn State somehow this one
Spiritually with us.
This could be part one. Part two could be.
They will show up on slides.
Yeah, okay. And then part two when we can get John here. So first of all, I want to say thanks to both for the invitation to come and visit you all, and both visiting with friends I've met in the past and making many new friends, which has been really inspiring to me, giving me a lot of ideas. It's been a delight to be here. So truly thank you for the opportunity. And I've also been inspired about how much the projects that are going on here on the AI problem that also give me ideas and new challenges for how we can take the mechanisms such as radiative feedback into this phase space. So first off, maybe what I say is, so the title has been my journey of trying to isolate direct from indirect mechanisms, in particular, as you all know, at least if you saw my presentation on Tuesday, from the radiative feedback, cloud radiative feedback, but thinking about this also, I think it's a challenge more generally when we're in a nonlinear system. Mechanism denial experiments are very valuable, but how do we separate these things? So really, this has been a journey of, you go into something like radiative feedback, you might have a TC simulation, or maybe we complicate it even more and we have global MPAS aquaplanet simulations. And how can we simplify it down, bring it back to basics, and come up with a simpler lesson? So it's sort of taking the Wayne Schubert approach, which always sort of reminded me how much of a joy it is to be a student in the classroom. And I think that's the fun of this research problem, is you first get overwhelmed by the complexity of what you study until you take the time and patience to find the simpler story that hopefully reveals itself. So the key question, well, that's already in my title. And I'm specifically thinking about this in the context of the cloud radiative feedback. So I'm going to use the same phenomenon that I presented on Tuesday to sort of explore this question. And in particular, one of the places where this feedback has been sort of difficult to separate out these effects. I'm going to keep with the theme and share some photo of well, both my group, but also extended beyond my group. So we were really fortunate to have, it was a small kind of ad hoc workshop with our NSF project, which is focused on cloud radiation feedback. You'll see some familiar faces there on the left. So we were really lucky to have some folks come down from CSU who are thinking about radiative feedback on very different scales. Eric Maloney is up there in the back row, and Levi Silvers, who was my TA for my first class when I was a Wayne Schubert student. And then, of course, Michael in the front standing next to me. And I'll mention also, Yunji Zhang from Penn State. He's a co-PI on our project. And then Rosimar Rios Berrios. And she's been really invaluable behind running the MPAS experiments. And then this isn't my whole group, but this was at least the members of my group, two masters and two PhD students who were with me in Boulder for that trip. And I hope they get to meet you. I am sure they will get to meet you at some point, and I hope you all, we can all come together and all of our groups grow through more collaboration. So the way I've tried to bring it back down to basics, I guess we could say. This has been my my circle of trying to, is this a simpler problem than I think? So we're trying to isolate some direct effect, which for me, I might say just very broadly right now at the moment, let's say the response of convection to, in particular, some term R, which we'll say that's the radiative feedback, right? And I talked about this radiative feedback parameter, which we can express as the ratio of the long wave cloud radiation forcing, so watts per meter squared radiative forcing due to cloud normalized by precipitation, or the total latent heating, so the latent heat times precipitation. And so that represents our R, the variable that we want to change. But then we have this term B, another variable that our A, the convective response, depends on, which is also dependent on R. Right? So we see some familiar math coming down the way, of course. If we have these two things, we can chain rule it out and expand out the dependence of A on R into the total of some direct effect. I'll mention this in a moment. We have the partial derivative with respect to R, and so that's assuming B is fixed, or let's say our indirect factor. And then we have the dependence of A on B, and then the dependence of B on R. And in the way we are actually running these experiments, R is not some continuous variable, but we have model experiments where we have R basically on or off, right? So it's really a 0 or 1. But we could think of, so basically re-expressing that equation in the way we actually have our numerical model data is something maybe more like this. So our delta A is given by, well, a slightly different delta A, where this one is assuming somehow constant B, right? So the changes in A with respect to constant B, and then we still have to grapple with this dependence of A on B that gives us an indirect effect, right? So the direct effect is really how is A changing due to the change in R, if we can somehow ignore or account for B and hold that fixed. But the total effect on A also includes this second term here, the indirect effect. And in this context, the large deltas, I think we can think of this as simply the difference in our variable A or our variable B from one experiment to the other, right? And it's the other terms and their combination that we have to take some work to try to identify. Right, so our experiment again is basically with and without R, or R set to 0 or 1. So in the meteorology we're thinking about, to try to put this in a nutshell back to what I presented on Tuesday, the hypothesis I've been thinking about and what we think the evidence is telling us so far is that the long wave cloud radiation forcing, so in essence all of the red that is affected not only at cloud base, but all the way through the lower part of the column. The long wave cloud radiation forcing increases precipitation efficiency, so you get greater lifting motion and moistening per unit convection, right? So higher precipitation efficiency associated with suppressed drying from stratiform downdrafts. And in other words, if you have more moisture, a more humid environment per unit convective precipitation, you have a more supportive environment for convection. And we've seen that in the response, for example, to convective cluster size, and then the frequency of convective clusters, they grow. So where we stand right now, as far as the different experiments we have and the different model frameworks we have, we feel quite confident about that message I just summarized, at least from the context of several WRF simulations that we have of tropical cyclogenesis. And then we have these simulations using SAM, these 2014 simulations that Alison Wing ran of self-aggregation in RCE. And so we see that mechanism response to the inclusion or removal of radiative forcing quite clearly. So I think we have a direct effect there. But our MPAS global aquaplanet simulations present a different kind of challenge. And at least as far as I can tell now, there's certainly indirect responses going on. So there's probably also indirect responses in the WRF and the SAM frameworks, but perhaps it's a more constrained problem. Whereas in the aquaplanet simulations, we have changing climate, basically, when we change the radiative forcing. And so that's what's motivated me down this path. So I'll talk mostly about, I've never presented this stuff, by the way. So this has really been like recent thinking and recent playing with data frames of large quantities of clusters from the MPAS output. And you're seeing in real time me trying to think through and see if we can make sense of what's going on. So we have these global MPAS simulations, which are, they're quite simplified. So it's an aquaplanet with constant summertime, northern hemisphere, summertime sea surface temperature. So TC season is what we were aiming for. And it's a zonally symmetric SST. And so we have realistic global rotation and with an SST maximum north of the equator, zonally symmetric. And we've run these simulations for 6 months, but really a lot of the response, including direct and indirect, happens within a couple days. And I actually don't need a very large data set to try to identify these confounding factors as well as the direct factors. So we have a control simulation, which is just radiative feedback as in nature to the best we know, where clouds and radiation are fully interactive. But then we have these two sensitivity tests, which are basically two different versions of R turned off or removed cloud radiation feedback, at least. So in HOMORAD, we're homogenizing the radiation in the zonal dimension, so longitudinally averaging the radiative forcing at each time step, but the radiation is allowed to evolve dependent on the cloud field and moisture and so forth. That ran away from us, and we had a different climate, so we've been playing whack-a-mole and trying to see if we could keep things from running away. So we had this second experiment, ClimeRad. And here what we did was we imposed the zonally symmetric radiation from the control simulation. Alas, again, the climate ran away from us, at least to some extent. And so Rosie has been chasing her tail to some extent and has run, I think, at least one more experiment than has gotten into this list so far that I haven't looked at yet. But yeah, so we've run these for a long time, but actually I'll focus on a very short subsample of output. And then of course the simulations have the same physics otherwise. So, and just to give you an example snapshot of this, did I mention so they're 3 kilometer approximately global simulations with the irregular MPAS grid mesh. And what I've done is impose this column-based, hydrometeor-based cloud classification scheme, which is identifying either non-raining or deep convective congested shallow stratiform and anvil clouds. And as in Tuesday, I'm going to focus a lot on the stratiform and the anvil. And I was quite excited to see that the classification scheme worked what I thought reasonably well. I mean, not just from this snapshot, but I've looked at the vertical motion profiles averaged over the different categories. And we see what we would expect, for example, the sine wave for stratiform and so forth. So I'm going to give you some quick examples of the climate, the challenge, so what's drifting in these simulations, at least from one of the sensitivity runs. So here's just the zonally averaged precipitation rate. So we're seeing the ITCZ, and this I think was averaged over the first 2 months of the simulations. And what you see is when the radiation's homogenized, the ITCZ intensified. This was actually counter to our expectation because we've always thought of the ITCZ as something that radiative feedback should be actually focusing and perhaps intensifying. So there's something else that happens, and we think it has a lot to do with the equatorial wave response. So controls on the left, the HOMO-RAD experiment on the right, and I think even without doing the wave number frequency decomposition, you can see very clearly from a Hofmahler over the equatorial region what's going on. There's both more intense rainfall in the homogenized run, and it's also very strongly organized. And when we do the decomposition, we see a greatly increased contribution from Kelvin waves. So that's the light gray bar on the right here. So the decomposition of rainfall, filtered variance, you see a much stronger Kelvin wave response in HOMO-RAD.
So the speed is slightly different. Is it?
That might be, we haven't looked at the phase speed of the Kelvin waves, but it could be, yeah. We probably are changing the lapse rate between the two climates. Yeah.
But you don't see this roughly gravity wave on your HOMO-RAD simulation.
Yeah, I think at least in the Hofmahler, well, this is only a subset of, looks like 50, 60 days or so. But the Kelvin wave signal, so one thing, yeah, the one thing that Rosie tells me, and I wish she were here to answer to this, but the way it's described to me is that MPAS really likes Kelvin waves. For some reason, the dynamical core of MPAS is very favorable to Kelvin waves. It could be that it damps other modes. And at least in the convectively coupled, we see that. The Kelvin waves are very excited. But what was interesting here is even though we see that drift of the intensifying of rainfall when we remove the cloud radiation feedback, when we look at the tropical cyclone breakdown between the two simulations, so in all of these I've got control on the left and just the HOMO-RAD experiment, so I don't have the other one here. We're still doing the statistics on the other runs. We do see a pretty dramatic decrease in hurricane intensity tropical cyclones, and then if we specify for major hurricanes, a pretty significant decrease in their count. And just in general, a very small count of Category 5 hurricanes. So similar number of total tropical cyclones, but the ones that become the most intense seem to be limited. And we have much more analysis to do to try to prove this, what's going on here, but this was a first hint, at least, that radiative feedback may be playing a role here in favoring their upscale development and intensification. The other thing we see is that when we remove the CRF, CAPE is dramatic, well, maybe it's not so dramatic, but very clearly when you average over time and average over longitude, intensified CAPE when you remove cloud radiation interaction. And now I'm showing you both of the sensitivity simulations compared to control. CAPE is shown in the dashed line, so that's our subsiding branch. But in general, the biggest signal that I see is an increase in CAPE almost everywhere, at least where there's the most frequent convection from roughly like -5 to roughly 30 degrees latitude. CAPE is intensified. And so, what's that?
Why?
Why is the CAPE intensified?
Why?
This is something that I'm still working through. What I can say for sure is it's very consistent with if we do this in an RCE simulation, and I've done this in my my tropical cyclone the limited area model, WRF domain simulations, I've seen the same thing. And then Rosimar's 2020 paper, she did a different kind of experiment where she completely removed the radiation with a Rankine vortex initialization. So it's quite different from just the cloud radiation feedback experiment, but I think the response was for similar reasons. CAPE was dramatically intensified when she removed radiation. So more intense CAPE, even though it would tend to kill the tropical cyclogenesis or delay it significantly. And as far as I've interpreted up to this point, I think it's really strongly tied to precipitation efficiency. So when you have the coupling between convection and radiation, and you have more efficient convection, precipitation efficient, you are basically exhausting CAPE more effectively. And so when you reduce the precipitation efficiency and then convection struggles to develop, it requires higher CAPE to get a given amount of convection. And so, in other words, I guess you could say the RCE balance, the RCE equilibrium state requires higher CAPE to have the same amount of convection as in the radiative feedback experiment. But
it's interesting. I think it's other radiation and the precipitation efficiency that seems to be the key.
Yeah.
And I always wondering this. I mean, we talk a lot about the RCE and this 40 years old thing. I think it should be updated.
Yeah, and we still learn a lot from it.
Yeah. We learn a great deal from it. Yeah. I think the model now needs to be updated with all these things.
Yeah. Yeah.
It's very interesting. Thank you.
Yeah. And and so far, what I speculate, again, this is ongoing analysis, but if we have higher CAPE, what I'm wondering is if Kelvin waves are taking advantage of that. And the Kelvin waves are intensifying by virtue of higher CAPE in the equatorial zone, as well as, in our ITCZ region. But I have to validate that. That's basically it's a suspicion at this point. So this is what we have. The CAPE is intensified. And so what I've been thinking about is, can we isolate the direct response of convection to the change of R and this indirect effect response of convection to what we could say clearly this is a change of climate in some fundamental way to the change of R, which then in turn also affects convection, our direct effect, or our factor A. So actually I wrote that wrong. That's not direct A, indirect B. It's mechanism A or response A. I need to rewrite that. So ignore direct, indirect. But the indirect anyway is how does convection respond to the change of climate due to the change of R? So what I'm playing with here, because we see this big change in CAPE, it's a change anyway. Because we see this change in CAPE, I'm playing around with the idea that our term B actually could be represented by CAPE. And so there could be multiple different ways to, let's say, or different ideas for what we should set B to. But I guess you could say we're exploring the idea that the differences in climate and the responses of convection through climate to the change of R could be sort of encompassed by the change of CAPE. So what I'm doing up to this point is, the method is relatively straightforward, just turns out to be a beast because you're working with MPAS like 80 million grid point data. But I identify instantaneous clusters, so objects that are contiguous in space of the distinct cloud types from our cloud classification, which I've already introduced, at least sort of the result of it. I haven't talked much about how it works, but and then I'm assessing the statistics and the behavior tendencies in these clusters and their changes across the experiment, but now trying to explore if we can basically set different dimensions of that response and learn something more. So I'm actually only analyzing 3 days of simulation time with it's 4 time steps of output per day. I've looked at much longer time series of data, and I find that you actually just don't need much to see the signals that I'm going to show you. It's quite consistent across the board. So now I'm going to overwhelm you completely with box plots, and I'll try to step through what we're looking at. So the x-axis, so we're looking at a histogram in this case. X-axis is latitude. And then the y-axis, so that's just a count of frequency. And in the top panel, I'll focus your attention on that one first. That's our deep convective clusters The bottom panel is this so-called DSA, so it's the deep convective, stratiform, and anvil clusters. And the way I'm identifying those clusters is if the object is deep convection or stratiform or anvil. So it's identifying these larger clusters that are either of those three categories. So in some sense, it represents kind of a quasi-MCS category, but I don't impose a size constraint or something like that. That falls out naturally. So histogram of the deep convective clusters, and I've aggregated these, of course, across longitude. I've aggregated them into our 3 experiments by precipitation or cloud classification, of course. And what we see when we go through our ITCZ region, well, you could see that most of the clusters are in the deep tropics north of the equator, where SST is highest. But you notice that the control simulation actually has slightly greater number of deep convective clusters than in the either of the 2 sensitivity simulations. All of the changes I see are quite subtle, but there is a change. And if we aggregate across now all latitude, you still see this difference. And the means in these distributions are shown by the white dot. And then I've done a statistical significance comparison of the populations where the first just 1 star is 95% from a Mann-Whitney test, or no significant in the case of DSA. So what's interesting here is we see this change in the control simulation, a greater number of deep convective clusters. But now if we look at these larger clusters, which I'll validate in a moment, at least aggregating across latitude, there's no significant change. But then you do see some latitudinal dependence where, at least in this, let's say, near equatorial region, we do see a more frequent clusters DSA in the control. Okay, cluster sizes now across the same latitude range. And so again, what I'm showing you here is deep sea, but now I've decided the stratiform was more interesting than the DSA, so I've switched it to that in the bottom. And here we see a big latitude dependence, but in an opposite direction. We see the cluster sizes of deep convective clusters are actually increasing when we remove the cloud radiation feedback. And we could call this the Kelvin wave zone, so our ITCZ band. But notice that as we get through cross around 5, 7.5, 10 degrees of latitude, we transition into it's quite a dramatic change of signal in terms of you can very clearly see with the naked eye that the control has larger deep convective clusters than in the sensitivity experiments, right? And then aggregating across latitude, we also see that basically these higher latitude, the farther north signal appears to dominate. And then in the stratiform, a relatively consistent thing where we see either an increase in stratiform cluster size when we remove the radiative feedback, or maybe little change, but then as we get up to this more northern band, we see quite a big difference in their sizes. And the way I've actually done the cluster size is it's from the cluster area as meters squared. I take the square root of that. And so basically it kind of represents like one length scale of how big these clusters are. And you could see that, well, in general, the stratiform clusters are larger than the deep convective clusters. And then the DSA clusters are even still bigger, which I'm showing here. So some of these getting up to, well, at least the top percentile here, up to almost 30 kilometers. So a consistent story here, increase in DSA cluster size in our sort of Kelvin wave ITCZ band, but then we transition into this regime where the clusters appear to be largest when we have the radiative feedback, right? And then here, although my eye suggests that there is a difference in population, it doesn't show up to be significant from the Mann-Whitney test. So next up, let's look at the precipitation efficiency. And I've actually calculated this from this method. So using the vertical mass flux masking for downward or upward, and specifically when I'm over either a deep convective cluster or so forth, any of these. And again, just as a reminder, this it's written in different ways, but what it microphysically represents is the fraction of condensate that translates to precipitation, right? With the residual of that being how much is evaporated. When we look at the precipitation efficiency, we actually see it is a noisy metric, and so there's differences between one latitude band to another. But if we look closely, especially at the means of the distribution, the white dots, there appears to be a slightly higher precipitation efficiency most of the time in the control when we have the radiative feedback included than when we don't. And for some reason, in some of these latitude bands, specifically the HOMO-rad simulation, the orange, appears to be the biggest drop-off. But we do see a statistically different population with greater precipitation efficiency in deep convection in the control. And then similar story from stratiform, so I won't step through that.
So James,
Yeah.
for the stratiform figure, you see a negative precipitation.
Yeah.
Is that indication of more evaporation, sublimation?
Exactly. So at first I said, uh-oh, there's something wrong with my metric. But actually, yeah, I think it makes physical sense. And I see this even more with anvil. It's often negative, commonly negative or around 0, which is an indicator that there could be more downdraft than updraft in those cases.
In your calculation, you do a vertical column integrative variable.
Yeah.
So you do not consider a horizontal.
Correct.
Okay.
Correct. Yeah.
That makes sense.
Yeah. So it can't be negative over the entire domain. But in this case, yeah, if we're just looking at the stratiform or anvil, we see the lower values here, which makes physical sense, whereas for the deep convection, it's generally relatively more narrow around a high precipitation efficiency. So most of it produces precipitation.
I know there's a difference in the deep sea and stratiform, but one with a weaker PE, larger area, the other is shown PE, but if you times the area together to look at just the rainfall amount, what's the difference?
Just the difference in precipitation.
Because usually we stratiform is weak, right?
Yeah.
So I think Dick Johnson was showing this 50-50, that type of thing. So it's low frequency, but it's a large area.
Yeah, that's true. So the area represented by the stratiform are much larger.
Larger, so
Yeah.
maybe a combination.
Yeah.
And that rainfall amount difference, at least from this will tell you maybe some information about how much heating project on the different vertical modes.
Yeah, that's true. Yeah, I think so. And then the last latitude slice, just looking at this now in the largest category, the DSA, so now you fall somewhere in the middle range of PE, because now this is averaging over basically all deep convective stratiform and anvil area. Again, we see a consistent signal, not in every latitude band, but generally a higher precipitation efficiency in the control simulation, but with the greatest difference around these higher latitude bands. And it shows up to be a significant difference when we cluster across all latitude. So the convective systems appear to be more frequent at most latitudes, but cluster size appears to have a strong latitude dependence, where they appear to be smaller in the equatorial, let's say, Kelvin wave band, and that's when we remove the radiative feedback, and then larger at high latitudes. Or sorry, I have that backwards, but it's not written there anyway. Smaller cluster size when we include radiative feedback, and larger cluster size when we include radiative feedback at higher latitudes. So we have this sort of intercept where the response appears to differ with latitude. And then PE is higher, again, when we include radiative feedback. That appears across most latitudes. So bringing this back to the whole mechanism I tried to sort of start with is that at higher latitudes, we do see an apparent coupling, or let's say a proportional relationship between the change or sensitivity and precipitation efficiency with radiative feedback and convective size. So perhaps this is evidence at higher latitudes, at least, of this direct effect. So how do we now isolate and try to see how this mediating effect is playing a role. So the last thing I'll try to show briefly here is we're going to try to examine if CAPE could be treated as our factor B that's acting as, let's say, the mediating factor, right? Or what's the word? I'm forgetting it right now. Conflating, I forget it. Mediating factor. So basically, in order to do this, we just treat CAPE as a dimension now, and we look at, as a function of, or let's say for a given value or bin of CAPE, how do these variables depend on the radiative feedback, right? And so what we're trying to look at now is trying to isolate this delta A with respect to constant B effect. And we can do this from a data frame sort of context. So now I've got CAPE as my x-axis, and again, we're looking at the histogram of clusters, the deep convective clusters here. And one thing I'll mention is that a lot of the clusters for deep convection, for stratiform, for DSA, they actually tend to have quite small CAPE, and it's a much lower frequency of clusters that have high CAPE. And I think this is just because on the timescales that we're looking at, we're seeing areas where the CAPE has been exhausted in general. So we see a lot of clusters, the majority of clusters are in small CAPE region where they've begun exhausting the CAPE. But what you notice is that there's a higher frequency of deep convective clusters for a given CAPE bin when we have the radiative feedback on. And that trend appears to go away or weaken as we get up into the higher CAPE regions. And I think this is basically, so up in this zone is where we're seeing the bigger impact of the change in climate, the intensification of CAPE when we remove the radiative feedback. But what dominates when we aggregate across the X dimension is greater deep convective clusters when we include radiative feedback, right? And analyze that comparison for a given CAPE bin is how to interpret that. And then now looking at the convective cluster sizes, and I'm showing you stratiform in the lower panel, we see across most of the CAPE bins, but especially the very frequent bins, which are in, let's say, the lower half of the x-axis, greater convective cluster size when radiative feedback is included, with a downward trend in our other sensitivity experiments, a downward shift when you remove the radiative feedback. And that shows up in the aggregated result on the right. And same thing, but perhaps even more pronounced in the stratiform cluster sizes. Larger cluster size for stratiform when we have the radiative feedback, again, with respect to a given CAPE bin. Right? And this response shows up for all CAPE bins in stratiform, quite clearly to my eyes. So, and then finally looking at precipitation efficiency, I think this is my last result. Precipitation efficiency across this dimension, we also see a downward shift when we remove the radiative feedback across most or perhaps all CAPE bins. And aggregating that, we see a statistically significant drop when we remove the radiative feedback. And I show ANVIL just because this also shows a really clear demonstration of that shift. And actually increasingly as we go up to higher CAPE regime. So for fixed CAPE, what I think I can say, the way I'm interpreting this, for fixed CAPE, so perhaps as our factor B, we've reconciled the effect of cloud radiative feedback R on our target response A, which I've been analyzing the cluster size and its relationship, proportionality to precipitation efficiency. Right, so this delta A with respect to a given value of B or bin of B. So the message here, at least from this analysis from our MPAS simulations, is that this direct effect, so our delta A sub B term, includes the proportional change in deep convective size and precipitation efficiency increases in these two metrics for, let's say, an increase or including radiative feedback for a given value or bin of CAPE. As well as perhaps, and this I think I'm being a little more provocative, we have more work to do to assess this point, perhaps also the change, the response we're seeing with the number of strong TCs. I suspect, at least based on previous tropical cyclone radiative feedback research, that the response in tropical cyclones is also owing to this coupling between PE, convective size, and radiative feedback. So just leaving a couple questions that I still think are very much worth kind of discussing and thinking about. This is just one thought process in how do we identify and isolate key mechanisms that act as B, the mediators or conflating factors in the feedback response to a given forcing such as radiation. How do we isolate these mediating or confounding effects? And then how does the nature of radiative feedback, this is I think a question that also has come up and comes up in all of our heads, how does this feedback depend on scale? Because clearly we're seeing a big dependence on scale, in particular of whether or not, or perhaps how strong mediating factors like B are, how strongly they appear. So that's what I've got. Thank you. Welcome any comments.
Thank you so much, Jim. I think I'm kind of stuck at the difference in climate between the simulations. And do you see there's like a very different meridianal flow between the simulations? And if it's possible to have the meridianal low-level inflow of energy as your D rather than K?
I don't know. I'd have to think about that. Yeah.
I have an even easier question.
That's I'll have to think about that. Yeah.
So in your homogeneous radiation, so do you mean by latitude dependence or global dependent, global average?
When we impose the radiation in that experiment?
Yeah, so how do you homogenize?
So yeah, so it's zonally average, so it still has dependence on latitude. Yeah. So it still varies with latitude. Yeah. Does that make sense?
Yes, but how does that vary in economic scale? I mean, if you look into more narrow band, how does the variation of that radiation?
Okay. You're saying, do I have a sense of how strong the dependence is on latitude? Yeah, I don't have a figure for that, actually. Yeah. Well, maybe what you're getting at is, could this be having a strong feedback? Yeah, and I think you're right. And that was why we tried to do the climb rad. Actually, Michael, when we were in this workshop at NCAR, suggested this idea that maybe it is what you're getting at, and I think sort of puts it in a compelling way. When we zonally average the radiative forcing, we're selecting a scale of radiative feedback because we still have radiative feedback in that simulation, but now we're only allowing it to happen in the meridional dimension. And so by getting rid of zonal radiative feedback, but allowing for latitudinal radiative dependence, we might actually be selecting something like ITCZ radiation feedback and actually amplifying that. So we weren't thinking about that when we tried that test, and we thought we would see a clean result, of course. But that's where I think the climb rad is at least a better comparison with the control. But we were surprised that we still even imposing the control radiation, that we see the same, basically at least the same like intensification of the ITCZ. We don't understand what's going on there yet. Yeah.
The second question is how do you calculate CAPE at the kilometer scale?
Oh yeah, as you know, there's a lot that goes behind that. So this is a big numerical challenge because we have to have the full vertical information, at the model grid scale, and I don't want to do this from spatially averaged information, so I wanted to have it at the native grid. The secret that I discovered was something called, are you familiar with Numba? The Python package Numba? So yeah, so I found some code from a recent graduate of Kerry Emanuel's he has a Python package that's published on Git for calculating MPI, so for calculating potential intensity, and that's built around a CAPE calculation. So thanks to his hard work, really, I owe a lot to him. He had built a CAPE routine into and leveraged Numba, which basically precompiles the function and treats it as something that can be run then in C or C++ to process it much faster. And then it processed the full domain CAPE calculations probably a factor of 10 faster than if I was just doing this like direct code. So I owe a lot to him for that calculation. It's not entrainment CAPE, so it's still more of a traditional CAPE calculation though. So that's one caveat.
So it's basically grid by grid.
Grid by grid, yeah, exactly.
NTUxOUxPennState also has the kind of the CAPE calculations, their package before. Yeah, that was I used that kind of more than 10 years ago. They have some of the package kind of released. I think it's a Fortran based maybe, but I think that right now so they have their new package that will be converted to the Python.
From which group?
I think the NCAL has released the CAPE calculation. It's a pretty long time ago.
Okay.
It's just directly just have the reading the like about output. It's usually like a user says the kind of what output they usually you can just use it the right way.
Ah, okay, yeah.
I think the problem may be MPI. So the data set's huge. You
Yeah.
need to
It's easy to calculate one column, but 8 million probably very challenging.
Yeah. I think this one's roughly 50 million grid cells or something like that. But yeah, my first attempt was trying to get Fortran code. And I have an old Fortran code that I had found from Kerry Emanuel had published on his website for calculating CAPE.
In this textbook.
Yeah, right, yeah. And then I was very grateful to discover this before I worked through coupling Python to Fortran.
But I think it's interesting to know where this high CAPE grids locate relative to the convective systems, the storms.
Yeah.
I think the original idea for CAPE is to represent the environment, but in a cloud resolving world, the environment can be created by the storm itself, at least at the snapshot sense. So how to interpret the change in CAPE can also be the other way around. Like that's actually showing you the feedback effects of the storms to the thermodynamics or the circulation. I wonder.
Yeah, I think I think about it in the same way, in the sense that we've changed something kind of almost microphysical scale, or at least mesoscale, by removing the radiative feedback. So I guess hypothetically at least, we've tuned a knob on precipitation efficiency, and we're seeing basically the different quasi-equilibrium state due to this change in convective behavior. But then I guess I'm thinking about it as sort of a two-way thing. So that's maybe phase one, and then phase two is perhaps the Kelvin waves and equatorial waves saying, aha, more CAPE, awesome, and they go crazy. And so we've changed the climate and intensified Kelvin waves, at least if this thinking is correct, due to the availability of more CAPE, due to the change in the convective behavior. Yeah.
Maybe kind of naive question. I think, well, surely triggering CAPE is one thing, but I always think of, in a classical way, there's no mid-level moisture formations there, but
Yeah.
that may be important, as you mentioned about the entrainment, and also
Yeah.
that information may be very important for the radiation,
Yeah.
regardless of how small amount it is separated.
Yeah.
So that's one thing, and the other thing is that I like to always think of, try to look at the convection. We have a matrix. One is a vertical forcing, and the other one should be a horizontal forcing.
Mm-hmm.
And the vertical forcing should be, no doubt, is cap,
Mm-hmm.
but the horizontal forcing may be part of the thing, the straightform area or wind shear or
Mhm.
that type of thing.
Mm-hmm.
But yeah, I don't know. I'm just curious about how if we look at the thing more in the more comprehensive view.
Yeah.
But still, I like you mentioned something about the column by column. I think
Mhm.
that's important to help us to understand much better. I
Mhm.
really, I'm not so sure, just one group, RCE,
Mm-hmm.
the type of thing. I think we learn a great deal from there, but it's already.
Yeah.
This is very interesting. So,
Yeah.
have you published this yet? Not yet. Still going.
No, these are fresh off the press results that I've been trying to think through. And I think some of my arguments are probably controversial even to my co-authors.
James, can you go
yeah.
back to your slides with DSA for the precision efficiency?
Yeah.
Yeah, I would like to know that's the difference.
This one.
Yeah, okay. You only account up to the 27.5 nodes.
Yeah.
Do you consider anyone further to the polar region or to the polar area or the 60 at least mean relative?
Yeah.
I
So.
want to see the difference between the PE from between the tropical region versus the relative region. That would
Yeah.
be more interesting.
Yeah, unfortunately I cut it off here, and the reason was when I was looking at the histograms, as pretty much like shortly beyond the 30-degree region, the frequency of clusters decreases dramatically. So the sample size is getting smaller, and I see much noisier results. But I could check that. Yeah, because I have it for the full, I started with looking at the full globe, but you could see south of in the southern hemisphere, it drops down to basically 0. And then that's also what happens if we go up into the 30s and 40s, is very few clusters. But I think what's happening there is we still have the clusters, but they're huge because of extratropical cyclones.
Yeah.
And it's registering these as these large, extensive clusters, basically of stratiform.
And I assume your MPES simulation did include some tropical cyclone, right?
Yep.
So, okay, as we see from the picture, okay, it's similar to satellite picture, right? So
Yep.
we will see some, big, very high precision efficiency associated with the tropical clusters and the tropical cyclone, if you have. Okay. On the other hand, see near the 60 nodes, there will be a polar front region.
Yeah.
There's another way to see high PE associated with the cold wave, cold front, warm front, those kind of stuff.
Yeah.
So imagine you should have this kind of twin peak.
Okay, yeah.
Right?
Yeah.
So it's another way to justify justification of your MPES result.
Yeah. Yeah, that's a
You know
great
what
point.
I mean?
Yeah,
So,
yeah. Yeah.
All right, us, everything makes sense, but
Yeah.
we need to have
We
some
could check that.
observation,
Yeah.
checkpoint.
Yeah. No, I agree. Yeah, that's a great point.
So especially for the mid-altitude verse.
Yeah. Yeah, it should look like reality.
Yeah.
Yeah. Yeah, that's a great point.
And if you don't have mid-altitude stuff, then how much we could trust?
Right.
Right.
Yeah.
Because tropical is very tricky. Right?
Yeah. Yeah.
It's also,
I have to check that.
So the water moisture source in subtropics and go both ways.
Mm-hmm.
But also in this aquifer, you see a lot of these long lines of
Yeah.
very sharp atmospheric river.
Yeah. Yeah, I think we're seeing evidence of atmospheric rivers and frontal zones here.
Yeah.
Yeah.
But this is aquaplane.
Yeah.
But what's the time? This summer or?
Summertime. Yeah. Northern hemisphere summertime.
May 6th.
So yeah, we could see wintertime storms, and I imagine if there were waves represented, there'd be very big waves down here because there's no land to block them. But yeah, so it's all extratropical cyclone dominated down here. And I need to find a different example because there are a lot of examples of TCs in this simulation.
Yeah,
I mean,
try one with
yeah, because I mean these, like using the tempest extremes tracking, we find roughly 130, 150 tropical cyclones, which is the first approximation, seems to be a decent comparison with nature. So I need to find a better example map that shows some of these. For example, I mean, it could be that this is an extratropically transitioning tropical cyclone. Need to look at some other time steps. Yeah.
There's any interest? You look at the intra-seasonal oscillation or anything?
As far as we can see, we're not getting a strong intraseasonal variance in these simulations. And it might be because we don't have zonal moisture variation. Like, for example, having the maritime continent. So having real continental geometry might support getting more intraseasonal variability. Yeah, I've asked Rosie about this too, if that's an experiment she's interested in running, where you have like a longitudinal warm pool also, not just in latitude. Yeah. That might give you what you need to get an MJO in this context.
I also thought about once you pass the maritime continent, to a certain thing, your boundary or whatever thing, open up to a free space. Before that was confined.
Yeah.
By the, kind of.
Yeah. Yeah, that's true. Yeah.
But still, it's interesting. Yeah, there's a zonal variability, so the casting.
Yep. Yeah.
In certain longitude, things are.
Yeah. So I think we're seeing a couple Kelvin waves here in these elongated features. That's my guess if we were to animate this. Yeah, Rosie has some nicer animations that I wish I could be able to show. But yeah, I might publish some of this story as part of kind of what I presented on Tuesday. And then ultimately these simulations would be fully public. And we might document these in a data publication, describing the experiments and how they were run, describing the output. But I also wanted to share with you all that I already had too much to show, but I'll just mention we're also in the process of running an ensemble of tropical cyclogenesis cases with fixed domain WRF at 1 kilometer spacing. So the idea is a lot of the previous work on radiative feedback with TCs, at least in like realistic context, has looked at weak shear situations. So like the typical conditions that are ideal for TC genesis. So we're trying to develop an ensemble that has increasing shear using real events. So we're going through the best track data set and picking storms that have stronger and stronger shear, and then using ERA5 as forcing to run these large domain TC genesis simulations. Each has a 10-member actually an 11-member ensemble, including the deterministic ERA5. So we already have simulations of NEPRTAC 2016. And this is just an example of the model domain on a 1 kilometer grid where most of the ensemble members end up producing a strong TC and some of them not. And to us, that's a big success. So there's nice ensemble diversity. And we want to try to analyze to what extent shear plays an impact on the radiative feedback. So we also hope to publish this data and we could share it with all of you. And if there are ideas for that you guys would want to use this data for doing these experiments using machine learning training, I think that could be really interesting.
Do you have, in the very beginning of your, that with the straightform of this account, you showed me one, right? Do you have the previous one?
The schematic or?
No, the simulation, the cloud.
This one?
Yeah. Do you have animation of this?
Of this one, no.
The time
Unfortunately, I don't.
I think
Yeah.
that would be also very entertaining.
Yeah.
For our scientists.
Yeah.
We look at this, how they evolve for
Yeah.
a certain period.
I need to generate that. Yeah. I have. I do have at least 20 figures of this, so I should make an animation
it's
of
good
this.
to,
Yeah.
I think, continue.
Yeah. Yeah.
You should choose the one with TC.
Yeah.
That will strike your eye and
Yeah.
see the evolving, see the moving.
I agree. Yeah. Yeah. Yeah, it's a great idea.
There should be plenty of TCs in your estimation.
Yeah.
Try one. Make a movie.
Yeah.
5 days or 7 days.
Yeah.
And all of that 7 days will also see the the frontal life cycle.
The frontal life cycle and the Kelvin waves
Yeah,
propagating.
that would be
Yeah.
great.
Yeah. Yeah, it's a great idea.
It's 10 times to
It
take it out.
definitely be
Yeah.
entertaining for us as scientists.
Yeah.
Like to see
Also
what-
education.
That's true.
Very
Yeah.
good.
Yeah, thanks for the suggestions. Yeah, I'll want to animate this. But yeah, I have to think about the how to maybe think about the meridional transport as the factor B, and maybe that could be a way. CAPE might come into play in that sort of feedback. Might be captured in a different way. I don't know. Maybe it would be a more direct approach to the indirect feedback.
One of the ideas popped up was you can do sort of a composite with storm center composite, so you can try to locate like the deep ones or the ESA ones, whatever. So based on the location, you maybe pick the similar latitudes, but multiple systems, and you average the structures and then the cave as a background, and maybe we can sort of observe the spatial relationship.
Yeah.
Yeah.
That's a
just
great
something
idea.
pop-
Yeah, looking at like the vertical circulation and how the environment's changed and how the structure changes. Yeah. Yeah.
And also, I know there's
Great
no
idea.
topography, but it's tempting if you look at this to the west, to the east of this simulation, right? The ITC is sharper, but to the west it's wider.
Yeah.
But I know there's no continent.
Yeah.
Still,
Yeah.
it's intriguing. Probably Alex will be very happy to
Yeah.
see the east part.
Yeah.
I remember you showed an idea like probably you see it, right?
Yeah.
Very idea like ITCD
Yeah.
really occurred. But it's
Yeah.
somewhat similar to
It does appear almost physical. Yeah.